Hello again, and welcome everybody to today's deep dive into test suggestions. We're very happy to have you today. My name is Lavinia, and I will be today's moderator. And in that role, I have some organizational information upfront before we dive right in. So the first point is we aim for interaction here, and the more the better. So if you have any questions on experiences, any comments, doubts, or anything you want to share with us, please do so. You can do that in the chat anytime. We have colleagues with us who will answer questions in the chat, and we will also moderate some of the questions to the audio track. And we also will have dedicated breaks for questions on the audio within the workshop and in between the parts. This all doesn't have to be well formulated, so if you have something in your mind, just go ahead and tell us. And also, if German is more comfortable for you, you can also ask in German and we will translate for you. And the second point is we always want to improve our workshops. And of course, for that, we need your feedback. So we will have 2 polls at the end of the meeting. One will pop up in Zoom and you can give us feedback directly. And the second one will open in the browser when you leave the meeting. And as I said, we would very much appreciate your feedback and a short note how you liked it today. So that was the organizational part. Now I will say 2 words about us as a company because we have lots of new faces here who might not know us. We are CQSE and we built a tool TeamScale, which you will see live in action today. And we are located in Munich in Germany, and I heard lots of people are joining near Munich today, but we also have offices in the US to serve our customers from Silicon Valley. So that was us. Now let's have a look at you. These are the logos from the companies that registered for today until last week. So there's even more today. And all of you proved that the topic we want to talk about today is very relevant across domains and technologies, which is how can we get fast feedback from long-running and slow tests. And with that, I'm very happy to have Raphael and Ramona with me today, who will tell you more about the topic and how we do research about these approaches and find solutions for it. So Raphael, the stage is yours, and go ahead.
Thank you very much. I will quickly take over the sharing and then get right into it. Perfect. All right. So modern software development is facing a bit of a conundrum. On the one hand, software grows, perhaps even faster now in the age of large language models. So meaning more code has to be tested for every single release. On the other hand, iteration and release cycles are getting shorter and shorter, which means we have less time available per test run. So we have to test more and more software or code in less and less time. And then there is additional pressure from coming from wanting to shift left. So this means we want to execute tests earlier in the life cycle. So instead of doing one big test on the main or release branch, we want to move a lot of the testing efforts to the feature branches and bug fix branches before the merge. This can be difficult to achieve for many of our customers with test suites that have been built over many years or sometimes even decades. And those tests can take many hours, sometimes days or even weeks to execute, which makes it seem quite impossible to execute them more frequently in the development cycle. Especially if easy possibilities like parallel test execution are already implemented and we are still looking at very long-running tests. Here, looking at the research can actually be quite helpful. There's an entire field called test selection or also test prioritization, where the basic idea is quite simple. We don't execute all the tests every single time something is changed, but we select a small subset of tests. This subset has to be fast to execute. And the tricky part, this small subset of tests has to be good enough to capture most of the bug detection capability in as few tests as possible. So we can detect most of the faults early and still have a big benefit from shifting left some of our testing efforts. Before I go into the topic in more detail, a few words about myself. I'm in the test intelligence team at CQSE. Our team handles all the different analyses and team scale that are concerned with software testing. This means either making tests more effective, so finding more bugs, writing additional tests, very targeted, or making tests more efficient, so finding the same bugs but using less time for that. I'm also a PhD candidate where I do research on exactly these topics. So this is also where most of our analyses come from. We either usually start them with student theses or research papers on these techniques before we decide to implement these approaches. And that's only one side, as not all of the techniques that work well in the sometimes very controlled environment of scientific research can also be applied in real-world environments. So all of these approaches that I present today, we implement in actual customer projects to make sure that they are applicable to real-world software with many different languages, APIs, endpoints, and so on. All right, back to the topic. So we are starting off with our big high-level test suite. Typically, these are not unit tests, but rather higher-level end-to-end tests, UI tests, sometimes hardware in the loop tests, where the hardware is also a limiting factor, or even manual tests where just humans have to do a lot of work to actually get test results. And these tests can take a lot of time to run. As mentioned, hours, days, sometimes even weeks. And this very late feedback causes quite a bit of mental effort, as I have a lot of changes at once that are tested. So the test feedback is very rough, very big scale for many changes happening at once. And also it's been a lot longer time since I've implemented my changes because the tests are not run as often. So the idea, let's take a small subset that we can run often and find most of the bugs early. To visualize this a little, we have here a set of test cases. So this is our test suite. Let's say each document here or each file here, file symbol, represents a test case. Some of our tests are failing. These failing tests are marked with the red symbol, the red X at the top right. And the failures are caused by some underlying bugs. The bugs are these little bug symbols. And the important part is now not every single bug causes exactly one test to fail, but some of these bugs cause more tests to fail. Like, for example, this blue bug represents the same fault in our code, and this causes these 4 tests to fail. The orange bug causes these 2 tests to fail, the purple one, only the single one. And that's one of the principles we can use, because let's say we make our test selection and select a subset of tests marked here on the left. And we find some of the blue bugs and we find some of the blue faults and one of the orange faults. And we don't have to find necessarily every single test case that would find this bug, but we have to find at least one representative. And this allows us to already start debugging and start fixing the underlying issue, and we don't actually have to select every single one of these test cases. On the other hand, there is something to note here. This purple bug has actually not been selected, or the test uncovering it has not been selected. This is a characteristic of all these techniques we are looking at. They are not 100% guaranteed to deliver all the same bugs that you would find with your full test suite. But with the approach that we suggest, we can still have a huge benefit from these techniques while detecting all the same faults. So we still run these tests just at higher intervals. Let's look at how this can be implemented. So we have here stylized an integration or main branch with this long line here, and we have changes coming in via merges from some feature branches or bug fix branches. And we have our big test run here marked with the green little dots, and they uncover a lot of bugs every time they run in big intervals. What we suggest now to do instead is to have this smaller subset of tests that we can run more frequently. And we can run it on the feature branches or bug fix branches. And optionally, we can also run it on the main branch in between the big test executions. And what we achieve with that is we shift most of the bugs to early in the life cycle. So instead of detecting everything at the one big test run, we detect most of the bugs earlier. The developers get feedback a lot sooner, ideally even before the merge. So while they are still working on the actual topic, they get feedback quite immediately. And we still keep an occasional test run of the full test suite. So the green test suite is still executed, maybe in slightly bigger intervals because we use some of the hardware for the smaller test runs, but we still keep the green big test runs. This means we don't actually lose anything because we still find the same total number of bugs. So just some of them will be detected later, or later in this case means in the interval they would usually have been detected. But for this to work, the essential part is that this subset is as capable as possible. And that's what the main part of this talk is about. I will present 4 approaches to select such a subset. And these approaches are divided into 2 categories. The first is a quality gate or smoke test suite. Here we select test once and then keep it for some time, maybe some months, maybe some weeks, and we keep it static. All my changes, no matter where they change things in the code, are run against the same small set of tests. And I only update once many new tests have been added or my code base has been changed a lot. The other approach is change-based selection. The idea here is to make a selection depending on what has been changed in the system. This means we select tests for every single change that has been made. So the test selection has to run for every single test run. This makes it a bit more effort in implementation, but gives more accurate results. And I have 2 techniques for each of these categories. So you can see how such a selection can work and what the advantages and disadvantages of the different approaches are. Let's start off with the quality gates. So as mentioned, of course, you get earlier feedback, but in addition, we see 2 other use cases where this is quite helpful. One is we have our big test run. As mentioned, in longer intervals, we still run a full test suite. And before we do this, we would like to actually protect it. We would like to check, is the software basically working? So kind of a smoke test run. And for this, we can use our small test suite, run it against our code base and see, does it work for the small test suite? If yes, we can go on to the expensive full test run. And the other thing I already mentioned is this running tests before the merge, so I can protect my integration branch or main branch. As there are usually many people working on the integration branch, a test failure there can hinder development of the whole team, while if I'm just working on my own branch, used for feature development or bug fixing, I only have I'm only hindering myself more or less with test failures. So having a quality gate that finds 80% of the problems that my whole test suite will find can significantly reduce the risk of introducing these problems on the main branch or integration branch. So let's look at these techniques. There are a lot of different techniques in research, and we have tested quite a few of them. As mentioned, we do theses and research papers. And I'm presenting the 2 now that we have found to work well, both in research and in practice. And the basic characteristic we're using for this quality gate approach is redundancy of historically grown test suites. This does not necessarily mean that there are many tests that do exactly the same thing, but that do very similar things. For example, I can take an existing test case, copy it, adjust it a bit to fit my new scenario, and a lot of it will still be the same thing, cover the same parts in the system. And if I want to spend as little time as possible on testing while finding a lot of different things, I can optimize here by reducing the redundancy. Let me try to give you a bit of a better intuition for this. I have brought an example project. This is Pixelitor. It's a Java application, open source, similar to MS Paint or a very, very simplified version of Photoshop. This is probably not something that many of you actually build, but it's something that everyone has used before. I think everyone has used at least some sort of image editing software in their lives. And it has an end-to-end test suite that is automated via the UI. So we can use this, and we are going to look at this for our test optimization. I will briefly explain tree maps as we use them a lot for visualizing this testing. So for those who are familiar with us or who know us, you will be familiar with tree maps. It's kind of like a map for your source code. So every one of these rectangles represents one component of the source code. The bigger the rectangle, the more lines of code are in each component. And step by step, I'm now adding a bit more detail. So we go one level lower and are looking at classes now. So every rectangle is one class in the system. It still holds the bigger the rectangle, the more lines of code are in the class. And one level further, we add methods. So now this is the level we want to look at. Every single rectangle here is one method in our source code and still holds the bigger the rectangle, the more lines of code are in the method. All right, now we are additionally adding some colors. And we are adding colors for one specific test case. We are looking at test Gaussian blur now. So this is one of the automated tests in the test suite of Pixelita. And we color everything gray that has not been executed in the test suite and everything green that has been run in the test suite. So everything that's green here is a method that has been executed in the test Gaussian blur method. Test Gaussian blur means we are looking at some kind of blur filter. It makes the image look fuzzy or less sharp, so applies some kind of blur. So this is the first test case. Now let's look at the second one. Test motion blur. You can already see from the name, it sounds very similar. And in addition, we colored something here for you. Everything that is blue colored now has already been tested by the previous test. So this means it's covered by test motion blur, but also by the previous test case. So only the green parts are actually new coverage that this test adds. And if we look at the third test lens blur, again, the name is already a hint. These are doing very similar things, and we can see it in the colors as well. We have very little green left. We have a lot of blue. Most of the things have already been tested. And this already gives us a first feeling of there is some redundancy. If we want to be very thorough, it makes sense to run those tests. But if we want to be efficient with our testing time, it might not make that much sense. Let's look at a slightly different visualization of coverage building up. Here we have a graph over time of how coverage is building up. So on the x-axis, we have the runtime. On the y-axis, we have relative coverage, so relative of the coverage of the full test suite. And this is not Pixelita anymore. This is one of our customer system in the medical software development. And what you can see here is kind of these staircases. So we do big jumps, and then we stay at the same level for quite a while. And this is when tests are executing new areas of the code. So we testing new things, and then a lot of tests will be in the same area of code. So what would it look like if we wanted to find a smart way to test efficiently with as little time as possible? Let's first look at the not ideal scenario. If we just execute tests from this block here, then all our tests will be on this staircase. We will have very thorough testing of this part of the code. But for all the rest of the code, let's looking back at this coverage, for all the gray parts, we will have no chance of finding any of the bugs that are in the gray parts. So this is very impractical for a change-independent set of tests. Now what we can do instead is we try to select a few tests from every step of the staircase. So we get a few tests from here, here, and here, and here. And we, with that, we have a very widespread testing over the system. What we essentially do is we reorder test cases. So the one that provides the most additional coverage per time is selected next. And if we select a small set like this, then we have a broad coverage over the whole system that has a good chance of uncovering faults. So let's look at what this actually, the actual effect in the test execution. We're starting off with our first test by the metric of selecting the test that gives the most additional coverage in the least amount of time, and it's test create and modify selection. Completely different test from before. And more importantly, if we look at the next test case, we get test change view settings. From the name, you can already hear this is a completely different area. And from the colors, you can see we have a lot more green left. So a lot more new uncovered, previously uncovered code that was executed now. And also looking at a third test here, from the name again, you can see this is very different, not only blur, 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 but we have a completely different things that are being tested. And still we have mostly green. There is, of course, quite a bit of blue because end-to-end tests always have some overlap. As we are just interacting with the UI, there will always be some things that overlap, but we can optimize for quite a bit more of additional coverage. And looking back at the chart from before, if we apply this optimization, so always selecting the tests with the most additional coverage per time, we get this graph instead. So by ordering the entire test suite like this, we can use only, for example, 5% of the time, and we reach almost 100% of the coverage that the whole test suite would provide. This means the more redundant a test suite is, the faster I can get to this 100%. And this is the basis of Pareto testing, which is the first approach that I'm presenting here. So the idea now is just take tests from the start of the graph and up to a point where you reach either a desired coverage or a maximum runtime that you want to have. And you have a good chance to uncover faults in the system wherever they appear. You might say, so far you've only been talking about coverage. The important part is actually bugs. Of course, you would be completely right in that. And that's why we did some analyses here. So we evaluated this approach in student theses and papers, as mentioned before. And we looked at open source as well as industry systems. Using both real faults and artificially seeded faults, we evaluated how much time do we need to spend. So how much of the whole test suite, how much time of the whole test suite do we need to spend to find 90% of the bugs. Important part, does not necessarily mean 90% of all the test failures, but 90% of the bugs. And what we got to was we can get to 90% of the bugs with 11% of the runtime of the full test suite. This is quite a big improvement, and what this allows us to do is we can not only run our test suite overnight or maybe every few days, but we can take this small selection and run it maybe several times during the day, perhaps even on all the branches, so on all the merge requests, depending on how many merge requests we have per day. Any questions on this approach? Otherwise, we would take a look at how this works in practice.
I have a question.
Yes, please.
So what you say here, how I understand what you're saying is that it's rather beneficial to focus on creating multiple smaller test suites for different areas of the code rather than, let's say, covering a big portion of the code, of a specific part of the code.
So the basic idea here is that we want to have widely spread tests. So this can be many small test suites, but we would even, depending on how your tests are structured. But for the basic principle is just to select a small subset. If you have UI tests and integration tests, for example, I would take a small subset of each of those and then run it against your changes. So basically, like you said, yeah, having a small test suite that you run more frequently and a big test suite that gives you safety that you run before release or like maybe on the weekend.
Okay. Thank you.
Sure. Any other questions?
Yes, I just want to make sure I understand how to read these stats here. Is it 11% as long as it's the right 11%? Or is it that you are running kind of randomly the tests the way you presented them, selecting them from different coverage sections? And you needed to get to 11%, and by that time you already caught 90%. So was this 11% selected randomly, or rather with that principle, but somewhat randomly, right? Or was it just that it was the right 11%?
These 11% were selected by this principle of taking the tests that add the most new coverage. So trying to cover the whole system as fast as possible. So by that principle, we need then the first 11% of the selection. So we can, by ordering the tests like this, we can cut off after 11%. And we've already found 90% of the bugs. That's the underlying principle, how we got those numbers.
Got it. So they were not specific to these bugs. They were just following that principle.
Exactly. So for specific test selection, we'll talk about that later. So for test selection that's more targeted at specific changes, those come later. But this was a general test suite that was generic and just can be run in a shorter time, basically.
Perfect. Thank you.
You're welcome. All right. I think we have one more raised hand.
Yes, question from my side. So you're speaking about coverage here and to select test cases based on this coverage. So I'm wondering, why do we have such redundant test cases there and this is coverage? So if we speak simply about coverage, then we do not take into account the dependency of the code fragment. So we have the redundance because we run them in different scenarios. And that would be totally out of the focus right here, right?
Yes. So, I mean, I totally agree with you that if you want to have like thorough, detailed testing, then these tests are not redundant. They are only redundant if we look at they test similar things. And if we have a bug that is like fundamentally breaks an area, it's very likely that not just one test will find that. And this is where we can leverage let's call it pseudo redundancy, like this kind of redundancy in the test suite that many tests cover very similar areas. And we want a fast test suite, so we just try to find bugs in as many areas as possible, basically. So while these tests might not be redundant when looking very low level, looking in a lot of detail, at a high level, we can say they mostly find similar bugs. And with that, we can basically get rid of a bunch of them or only run them in higher intervals. Some of those very specific bugs we won't find early, but many of the general bugs we will find a lot earlier.
Yes, that's one point. But of course, if I have a scenario where I have two classes calling ABC, for example, and then I have a test which is running that way, and the next one is ACB calling, then I have a different flow. And I think we all know that simple errors are often in conjunction to the scenario, so in a more complex matter to be found. And that would not be taken into account with this approach, I think.
No, exactly. So this is a heuristic. Yeah. It works pretty well, but does not cover all scenarios.
Thank you.
You're very welcome. Any other questions?
Yeah, we have one question in the chat, and I think we should go on then for time reasons. So the question is, will you show real examples like before and after, test suite A before and test suite B after?
So we have a little bit of a live demo here, but that's of course also not a completely real system. We can definitely, if you are interested, send you some infos on real systems afterwards. In this talk, we are only talking about the general accumulated numbers of multiple systems. So we are not looking at individual systems.
Okay, that was the right answer for the content. So go ahead.
All right, then Ramona, I would hand over to you for a quick demo.
Thank you, Raphael. I will just take over the slides. And here we are. So I will show you in a live demo now how this Pareto ranking actually works in TeamScale. Shortly about me, I'm Ramona, and I'm, as Raphael, part of the test intelligence team. And I'm mainly responsible for onboarding new customers and help them to get the most out of TeamScale. So in our live demo now, we will use as a demo application the digital bank, or short DigiBank. It's an open source digital banking application written in Java. And it offers all the functionality you would expect from a typical banking application. You can see your balances here, and you can deposit or withdraw money. So now let's switch over to TeamScale. As you can see, TeamScale is a server-based web application. We can either host it for you in the cloud, or you can have it on-premise in your own infrastructure, depending on your needs. So I will just log in with my username and password. And I'm here on the metrics perspective and the test view. But before I go into the details here, let's take a quick tour around TeamScale. So you can navigate through TeamScale with this blue sidebar here on the left. You have different perspectives depending on your chosen analysis. For example, you have a dashboard with all the key information at one glance, and you can highly customize it to your needs. For our demo today, especially the metrics perspective is important, and the test gaps perspective with all the smart test selection features for our DigiBank project. And you can not only have one project in TeamScale, but multiple ones, and you can navigate through them with this top bar here. So you see I have the DigiBank project, but also the Pixelito project that Raphael mentioned before. And within one project, I can select the different branches. For example, here I can switch to release branches or also to feature branches. So in our banking application, we see that we have in total 108 tests, and they take around 16 minutes to run them all. And we can have now a closer look into those tests. We see that they're divided into API and UI acceptance test, and we can also have a look at those. If we navigate further down in the hierarchy, we see a list of all those tests. And if we chose the first one in the list, we see here one of our famous TeamScale tree maps. So this test, the last time it was run, it passed, and it took 8 seconds. And in this tree map, it is shown which methods were covered when the test was run. So all the little squares are the methods in DigiBank, and in green are the covered methods. And you can also see here the test execution history. So now you know how TeamScale visualizes tests. So let's switch over to the Pareto analysis. So for this, I go into the test gaps perspective and the test selection. And here we have our risk coverage tree map. It's still completely gray because we haven't selected any tests yet. I will do this with the tab Select Tests, and I get a list of all my 108 tests. I can now filter those tests with custom queries or by name or other properties. And because I have only 108 tests in this case, I will select all of them for my analysis. So we're adding those tests now, and TeamScale will calculate live how the coverage behaves when those tests are executed in their default order. And we already see the risk coverage tree map changes. We see here in green again the methods that are covered by those tests. And here on the right we have our graph displaying the coverage over time. On the vertical axis we have the relative coverage in percent, and on the horizontal axis we have the total time. And we see that it takes 16 minutes to achieve roughly a coverage of 100%. And as Raphael described, we have here a little steps or plateaus. So relatively quickly we achieve a coverage of 45%. Then we have little steps here, a bigger plateau here, until we finally reach the coverage of 100%. So in my case, I would say 16 minutes take too long. In real world scenarios, we often see it takes hours or even weeks. And so I can go now and prioritize those tests to speed everything up. So I will just use all my selected tests and perform the Pareto analysis. TeamScale is now live calculating how this would change the coverage. And we see that it takes only 2 minutes, so 14% of the original 16 minutes, to achieve the same coverage of 100%. And if you now see, the coverage is really steep here, and we achieve the coverage relatively quickly. And if you say now, this is still too long for my use case, I want to adapt my test budget, you can use the slider here, and I will just drag it to the left to say I have only 1 minute time for testing. And you see how this risk coverage tree map changes. In light blue are all the methods that are no longer covered if I reduce my test budget, and in green still the methods that are covered. And we see it only takes 7% of the total time, so it's 1 minute, and we still achieve a coverage of 98%. So in a real life scenario, I would now execute those tests. I won't do this here for the demo, but I can save the list as a CSV for my testing pipeline, or I can save the list for later use. And this is how TeamScale performs the Pareto analysis. Before I switch back to the slides, do you have any questions about the real-life example?
Yeah, we have some questions in the chat. So, but the colleagues are answering them already, so I think we don't have to read them out loud. And we have one comment, a little bit confusing to call 100% test budget coverage, since obviously a lot of methods are not covered.
So that's why we call it the relative coverage. So you have the 108 tests that you are considering for your coverage. And from this relative coverage, then we are considering again what you would lose in quotation marks if you reduce your test budget further.
All right, thank you. So we have no more new questions.
Then I will switch back to the slides. So for our Pareto analysis, we need test-wise coverage, and we collect that with our Java profiler. And don't worry if you don't use Java in your project. We support many languages. So we have here a list of all the languages we've been working so far. And in bold orange, the ones that most of our customers use. So we have the most experience with those languages. And if your language is not on the list yet, just let us know afterwards about your tech stack, and we can have a chat about it. So now I will hand over to Raphael, and he will present further test selection methods.
All right, thank you very much. Quickly switch setup again, and then let's get back to our other approaches. So the one issue we had with this approach was that the input we need is this test coverage that we now mentioned a bunch of times. And actually, this is not only general test coverage, but it's actually test case specific coverage. which means it's a lot more data than regular test coverage. And recording it is some effort, as we need infos about every single test case. So we need to know when it starts, when it ends. And we do this with many customers, but it does make it quite a bit harder to get started. And additional things like if you have many languages, we usually need one coverage tool per language. And these tests start and stop signals depend on the testing framework and so on. So it is just quite a bit of initial effort and some continuous maintenance effort to get this started and to get it running. So the question we asked ourselves is, can we do the same thing, or at least a similar quality selection, but with purely static data, so not requiring any data that is collected while the tests are running? And our idea was the same. So we want tests from these different areas. So we want tests from different parts of this staircase. In other words, the tests should be as dissimilar as possible, as different as possible. And for this, we also tested a bunch of different approaches, and I'm presenting the one that we found to work best. So we want to find dissimilar tests, and our approach was first, in the previous approach, by looking at coverage. So we look at tests that cover very different things in the system. But similarity can not only be rated with coverage. If I show you a test case, for example, you can probably also have some intuition whether these tests are very similar or very different. So essentially based on the content of the test case. And that's what we want to do as well. We want to use the test content to judge similarity of two test cases or of many test cases. And to judge this dissimilarity of test content, we first need to quantify it. And in our approach, this means bringing it into a vector space. For bringing any text into a vector space is generally called embedding. And here we have simplified it quite a lot with 2 dimensions. So each dot here, which represents a vector, which is a test case in this scenario. And the important part here is that similar tests need to have similar vectors. So they need to kind of point in the same direction if they have similar content. And the way to turn tests into vectors needs to sustain this similarity. We'll talk about that in a little bit. So, but let's get into this. Once we have these vectors, how do we find these similar tests? From then on, it's actually quite simple. We just start with any test case. Let's pick the one over here that's marked with green. And then we just pick the one that's the furthest away by some distance metric. So in this case, let's say it's this one on the very end on the right side. And then again, we go to the one that's the furthest from the first 2. So let's say that's this one up here, and so on. So furthest from those 3, pick this one down there, and so on. As I mentioned, the important part for this to work is the embedding approach. There are very simple embedding approaches or very complex ones. The one we found to work best after trying a bunch of different ones was using LLM embeddings, so large language model embeddings. So these are essentially the vectors that large language models use to represent text internally. It's kind of the first step that a large language model does before it's actually producing text. It's creating an embedding from your input text. And here, very simplified example to help a bit to understand why this works. So in large language models, these vectors, of course, have way more dimensions. And here we have it very simple with just a few dimensions. And we understand one dimension as representing a certain characteristic of a word or a text. And the important part here is that this means that semantics are somewhat preserved. So the meaning is actually encoded in those vectors. The meaning of a test case, the meaning of the text is encoded in those vectors. And the similarity of the text is kept. So we have these distances between man and woman and king and queen. They are kind of like the same because there's a certain level of difference between them. Real LLM embeddings, as mentioned, are of course hundreds to thousands of numbers, and they carry a lot of semantic information. And we don't fully understand the meaning of individual dimensions in it, but the important part is for us is that it works. So what we do is that each test case gets its own embedding, and similar test cases have similar embeddings. And then we can apply our techniques. So we use as input our test steps in manual test cases or the test code with automated test cases, and then create embeddings in the model. We then calculate the most diverse set of tests that is possible, so the most distant tests. And in addition, we also consider the runtime because we want to prefer fast tests. We did the same thing as before, evaluating this on open source and industry systems and checking how fast, how much time do we need to find 90% of the bugs in the system that the whole test suite finds. And what we got to is we need 13% of those 19% to get those 90%. So we lost some of the performance compared to the 11% of the coverage-based approach. But we have the huge advantage that we don't need this coverage information anymore and only need static input to get started. And these additional 2% are not a very big difference, and we can still get our tests significantly faster and run them more frequently, run them on branches, things like that. So we can still get our test suite that might take some days to run down to an hour or a few hours, while saving a lot of effort because we only need the static information. All right, that's what we have about the second approach. Any questions about this one?
Yes, we have one question in the chat.
All right.
About, I think, the vector embeddings. And the question is, but would a random forest kind of classification not suffice for better explainability, maybe?
If you are aiming for explainability, then there are other categorizations that surely work better. We did try a few. We did not try random forest-based embedding. We tried things like word-to-vec. We tried some simple bag of words-based approaches. But yeah, we found that the large language model-based approach worked the best in our testing. That's why we picked it in the end. That might be interesting to try further ones, but yeah, we did not do that yet.
Much difference between just using the test steps to analyze versus using the code or using both?
Sorry, I did not fully get that acoustically. It was a bit quiet.
Oh, sorry. Did you find that if you use just the test steps as an input to LLM versus the test steps and the code or just the code, that the results are much different, or is it very similar?
So test steps we only really considered for manual test cases where it's actually a person clicking through the tests. So we don't really have that comparison. When we do automated test cases, we always include comments and any natural language data that might help. But we didn't really do that comparison.
Thank you.
Thanks for the question. Anyone else?
We have no more questions in the chat, so you can.
All right, then let's continue with the second big part of approaches. So far, we were always selecting a fixed set of tests. This is a bit easier to do because we don't have to build any make any dynamic changes to our continuous integration where we query things every time, but we just provide this fixed set of test cases. But if we can significantly improve performance by actually considering changes in our selection. And that's our second category here. Instead of running the same test selection every time, we select different tests for each change set. So for example, here we have for our first change set tests A, B, C, D, E, and for a second change set, we select different tests C, D, F, G, H. This allows us to be more accurate, and it works best for small change set and frequent test execution. But the good part is it also allows for executing tests more frequently. So it kind of improves itself a bit there, because we need smaller change set. If we do it for a whole release, it's likely that the whole test suite will be selected, because we just have so many changes everywhere in the system. So everything will be considered relevant. So this is really good for testing changes of a single pull request or a single push or a single commit in your code base, or even in the IDE if you want to do tests before pushing something and you want the tests that are relevant for you. And for this, again, we will look at two approaches. First, one with coverage. This makes it nice and visible and easy to grasp. And then we again look at a kind of cheaper, easier to set up variant that works without test coverage. The idea is basically we use test coverage as before as our input. So from the left here, we have test coverage. This can be from manual test cases where we record what a tester is actually doing live in the system, or from automated tests where the CI runs tests, and then we record test coverage there. And then we add the code changes. Code changes in this case we get from the version control system. This can be your GitLab or even SAP system, GitHub, whatever version control system you're using. We combine these, so we select only the tests that are relevant for your changes, and then you get your selected set of tests. And to give you a bit of an intuition on why this can be such a huge lever, I brought, again, a visualization with one of our tree maps. This is the same as before. Every little box here is a method, this time from our own system TeamScale. And in orange and yellow here, we have changes for one feature ticket. And in this case, it was support for a new Java version. So when a new Java version is released, we have to support it, which means we need to make some changes to our scanners, parsers, and other code that deals with the language. And in a second here, I will run an animation that shows how the system is covered. So things will show up in white briefly as they are covered, and then fade out to green, and we will show coverage accumulating over the run of our test suite. Let's get this started. And we can see here a lot of tests being executed, coverage building up in all kinds of, all parts of the system. And we can already see that most of our tests actually don't pass through any of the changes that we made, which does make sense because we, of course, on the one hand, did not foresee Java getting these exact new features. So we did not foresee any of the new methods being written. So there are no tests, no prior tests yet, no regression tests yet. And on the other hand, TeamScale does a lot of other stuff besides Java. We have a lot of other languages. We have a lot of other features. So most of the tests will not ever pass through this. In this specific case, it meant that 4 tests actually covered any of the changes. The 5,000 plus other tests we had at the time, we could skip. Which means we can save a lot of effort by not running tests that do not cover any of the changes. And that's exactly the idea behind test impact analysis, the first of the change-based approaches. We run only the tests that are relevant for the changes that happened in a specific time interval, usually since the last test run. And with this approach, we can actually get quite a bit more accurate. Instead of the 11 or 13% of test execution time, we can get down to 2%. So in only 2% of the test execution time of the whole system, we can find 90% of the bugs. And this means that we can turn a big test run that maybe can only be executed once every release or once every few weeks into something that can run before every single merge. And that's a huge lever for our shifting left and allows us fast feedback times and developers to have personalized feedback for their own changes. Very quickly, before we again look at a demo for this specific analysis, any questions?
We have no questions in the chat so far.
All right, then I will hand over to Ramona for another demo.
Thank you again, Raphael. So now in this demo, I will present to you the test impact analysis in TeamScale. And for this, I switch roles. I'm now in the role of a developer, and we will use again our Digibank application. So now I'm the developer, Andrew Smith, and I got this issue assigned from my product owner, Mark, and it has an issue number and the title Add Quick Save View. So in the description, it says that this new feature allows user to easily save €100 or dollar to their savings account. And I'm an eager developer. I used Claude Code to implement it, and that's how it looks like in the Digibank. So we have here this new quick save feature. And what is left is that I need to test the feature if all the implemented code is correctly behaving as intended. So I'm switching now over to TeamScale again. And we are back here on our test view in the metrics perspective. And just as a small reminder, we have 108 tests and they take 16 minutes to run. So I will now inspect all my issues. I can also see them in TeamScale. So I go to test gaps and issues. And through our connectors to your issue tracker, for example, here it is Jira, we can also see all tickets here. And I can filter those tickets, for example, with custom queries I can save for later. And here I created a query to show me all issues assigned to me. And in this list, you can also see that we have here this quick save view issue. And when I click on it, I see the same details as I see in my Jira ticket. So I see the description and all the other properties. So for TeamScale now, we can go a little bit further down. And we see here again a tree map. It shows me in yellow the files that existed before, but I've changed it now with my new implementation. And in red are the methods that I created newly for implementing my quick save feature. So how does TeamScale know which files were changed or newly added? This happens by the commits. So in each commit, I add the issue ID here in the commit message. And even if I push to a feature branch, then TeamScale knows how the commits are related to this specific issue. And now to test my feature, TeamScale has here this section, the test suggestion. So it suggests one test here that runs 18 seconds compared to the 16 minutes of the whole test suite. So it saves me 98% and I can get quicker feedback. And we will just run this test now in our pipeline. I've prepared a small script for it. So let's run those impacted tests. And what is happening now is that the Digibank application is built. Then TeamScale is queried which tests are actually impacted, and it will execute those impacted tests. And a little bit spoiler, it will not only execute this one test, but it will execute two tests because when I implemented the feature, I also implemented an additional test. And it was not executed before, so TeamScale does not know about it. But because I pushed it to the respective branch, it will be also executed. And here we see the window opening with the test runner, and it will now test our new quick save feature. So this was the existing test that runs now through, and it will shortly close. And then the second test will start, the newly added test. and also testing my new quick save feature. So everything cleaning up. And the window should close. So now we can have a look into the terminal, what happened here. And oh no, we see that there's a build failure. So the test failed. And we can have a look here in the console, but if your tests are running on a server, you might not able to see this. But we can go here in TeamScale to the tests view again. And then we see we have now 109 tests because I added an additional test and one of those tests failed. So I click here on filter and sort the tests by the result to get the failed test on top. And now when I click on this failed test, I can also see the console output here that might help me for debugging purposes. And we also see that it failed. It took 18 seconds, but it failed. And if we go further down, we see again which methods were covered by this test. And most important, we see a test execution history. So this test is not a new test I implemented. It was the existing one. And it was run before successfully, but then something changed in the code and then it failed. And we have here in this tree map the changes that are related to this test failure. So in orange, we have this method that was modified since the last test run passed, but now it is more prone to contain this bug that caused the test to fail. And we can inspect this method. So we go to see what changed in between those different states. We click here on method history for this transfer method. And we see all the respective commits and can also compare the different states of the file. You can see here this diff view, so line by line comparison, you might be familiar with probably. And if I scroll down a little bit, nothing changed here. But we can see here are two lines that have comments that didn't have comments before. So for debugging purposes, when I implemented the quick save feature, I commented those lines in and forgot to remove the comment again. So I now know how to fix the issue, and I will run a fix, remove the comment, and then the test will be executed again. I've prepared a script, of course, for that. What happens now is, again, that my fix is committed and the digibank is built and the respective related tests are executed. And I can see what happens here is under activity, we can have different times until we want to see all the commits. I want to see all commits up until now. So we see here, this is my most recent commit I just did to remove the comment. And if we click on this commit, we see which files I have changed and the test, the relevant test is starting again. And we see here what I changed and also the test suggestion. So only one test is relevant to my changes. And this shows you that this test impact analysis does not only work on issue level, but also on individual commit level or on merge requests or pull requests. So we should now, the test should be now finished. When we have a look, we see that everything was successful, but we can also see it here in TeamScale. If we go back again to our metrics and test view, then we see we have 109 tests, none of them failed and all were successful. So let me switch back to the slides. What we've just seen in this demo is that usually you would need to build your pipeline, your application, and then run the pipeline and wait until the pipeline finishes until you can get feedback. Now with the test impact analysis of team scale, we were able to build the application, to test it, to get immediate feedback that there's some defect. We were able to fix the bug and remove the comment. And then we built the application again, run the relevant tests and only the relevant tests, and saw that everything was fine. And this is the power of the test impact analysis, that we get faster feedback in shorter time, and we do not have to wait for the whole pipeline to run, because we are running only relevant tests for our changes. So this is all from the test impact analysis, and I will hand over again to Raphael.
All
We
right.
have one questions in the chat. We can
yeah.
just answer it quickly. So the question is, was just also wondering if there's a reinforcement learning possible on the model on the client side, or is it just pre-trained?
I'm guessing this refers to the AI test clustering. We had one before, so to the previous approach. For this one here, there is no learning involved at all, no artificial intelligence. For the models, we just used pre-trained embedding models from OpenAI or also local models like CodeT5. We didn't look into whether pre-training a model for this specific use case would improve performance yet. Does this answer the question, or were you referring to something else?
Yes, that answers my question.
Okay, thank you very much.
Great. So no further questions in the chat.
All right, then I will go on with the last approach. We saw live now the coverage-based approach for change-based test selection. And the last one is an equivalent approach, but this time without coverage again. As we have similar issues as before, just here they are even a bit more relevant, because we have this initial setup effort, and we actually need to keep coverage even more up to date, because we need to have it ready for every single change set. So this means similar problems, but even slightly stronger. So we tried again to find an approach that does the same thing, but with exclusively static information. And our idea here was we automate basically what I would do as a tester or developer if I have to find existing tests for some feature or bug ticket. For example, let's think back on the digibank that we looked at in the demo. We have some banking application, and we made changes in login, accounting, and search. So to find the fitting tests, what would I do? Usually do some global text search for logging, accounting, and search. And basically similar to a Google search. And search is actually a quite well-studied and understood problem. And it works well in search engines like Google pretty much everywhere. And compared to the search complexity that Google handles day to day when processing web searches with billions of web pages, searching through a few thousands or tens of thousands of test cases should be rather simple and doable. So what we do is we change the problem of test selection or test prioritization into a search problem. Basic approach, again, is rather similar. We get our input, the manual test steps or the test code, and we create an index this time. So we need to create some index that we can search later, which we'll call document.db here, and that contains all of our test cases. We then again get the code changes from the version control system. This time we process these code changes into a search query. So these changes are basically what we are searching for. And then we apply what we call similarity scoring, essentially just a search for our changes on our tests, and we find the best matching tests, for example, for a budget of 15 minutes. So we just pick the best matching tests until our 15-minute budget is filled. To give you a bit of intuition on why this works most of the time, here's an example. So we look at the test system Digibank again, and we have a function called transfer here. So this transfers money from one account to another. And we made some changes to this. And let's say we look at some of the keywords here. So some of the words that can identify things for us, like transfer, accounts, and amount. And now we go through the different test levels and see how these keywords reappear. So first, in a unit test, it's rather obvious. It's actually also code. So the keywords will appear as code. We have to somehow create an account. We have to make this transaction. So we actually have to call the transfer function, and we have to set some amount. So all of these keywords will reappear in unit tests. Then going one level up, we have here the example of cucumber tests, where we describe use cases. And again, we have to describe it that we somehow transfer money. We will have some accounts that are involved in transferring the money. And we have an amount field that needs to be filled. So again, we have the same keywords. One level up, robot tests, in this case for UI automation. So we again have the keywords transfer, account, amount appearing somewhere in the test case. And finally, for manual tests, and even here we have similar keywords appearing. We tell there is an instruction to open the transfer page. We select an account and we enter an amount to transfer. So these keywords frequently reappear in all different kinds of test levels. One thing to consider is that not all keywords are equally valuable. So some of the keywords, like new in Java, for example, should not be calculated as high or be as valuable as very specific ones, like the ones we just picked out, like amount or account. And to make sure that the correct keywords get prioritized, we use a technique from search literature. And that is a bit more, but the basic functionality is TF-IDF, so term frequency inverse documents frequency. Very rough, the description is that we use on the one hand term frequency. That means how often does a word appear in a test case? That is good. So if a word in our search, in our query, appears often in a test case, the test case will be ranked higher. On the other hand, we have the inverse document frequency. If a word appears in very many tests, so in all of the tests, like new, for example, we probably create new objects in most of the test cases, then it will be ranked lower. So we kind of, this reduces the score if a term is very frequent or appears in very many test cases. And this works very well to match code changes to test cases. After scoring a query with this TF-IDF or a similar approach, we then take the top test cases. So basically, you can imagine it like a Google search, and the first results are the most relevant. And the first page will be the best results. Page 4, probably nothing relevant anymore. And it's similar here. So the first results will be very relevant for your changes. The further back you go, the less relevant it is. While some words are probably still matching, but it's not very targeted anymore. So with this approach, we did the same evaluation as before. We look at how much time do we need to detect 90% of the bugs. And evaluating in a similar setup, we found that we need 4% of the overall execution time of a test suite to find 90% of the faults. This is twice the time we needed with test impact analysis, but it's still a huge improvement. It's still 25 times improvement over running the full test suite, which means we can still accelerate a test suite that would run for a week down to some hours and run it for individual pull requests or merge requests. So we now have these 4 different approaches. Everyone delivers somewhat different results. Which one should you pick? Let's look at this in this conclusion. We have our 4 approaches. 2 on the left side here are change independent. These are kind of quality gates or smoke test approaches. And 2 are change dependent. This means they select different tests for every single change set. Generally, we have an increase here from the bottom left to the top right. So this is the simplest approach. It needs the most amount of time to find 90% of the bugs. The further to the right or the top we go, the less time we need, but the more effort it is to set up. So test impact analysis will mean quite a bit of initial setup effort, but it delivers by far the best results, while AI test clustering can basically be run out of the gate, but you need some more time to run to find the same level of bugs. Which approach is the right one has to be decided per case. Approaches can also be combined. For example, we can do similarity scoring for pull requests. So on the branches, we run change-specific tests. So we run only the tests that are good for the changes that were made on the branch. And to have a general safety net in front of the big test runs, we run the AI test clustering, so the change-independent quality gate approach for the main branch. As I said, what is correct for your specific case has to be decided individually. And to help you with this, we also offer a follow-up workshop in, I think, around 2 weeks, where we explain how we typically set this up, how a pilot project might look like with doing this either with us or without us, and how you can integrate this approach into your own CI. So if you're interested in that, feel free to register. And with that, if you want any more information, feel free to contact us at any time. And we often hold similar workshops. We can also hold similar workshops to this in your company. And if there are no further questions, I would hand over to Lavinia for some closing words.
Yes, we have one question,
Right.
I think the search query. So let's take that one first, and then I will make a short wrap up, and then we can take the other questions. So who is creating the topics like login accounting to search for a LLM or a human? And who is analyzing all the sources of information?
All right, so this is basically what we do in TeamScale. And this is not AI or large language model based. This is basically search technique based. So this search technique essentially decides which keywords are valuable based on where they appear and how frequent they are. As I said, very roughly, it's this TF-IDF system where we reward certain tokens, certain terms, and punish some others. So these terms will be automatically extracted by a, in this case, not LLM or not AI-based system, but a classic search system. Does that answer the question?
Yes.
All right, perfect.
Great.
Yes.
Just a raised hand.
Yeah, thank you. Have you considered also using historical information, such as if change in this part of the code failed a test that's seemingly not related, but somehow was related, that you could use that information in the future?
Yeah, that has one big caveat, which is that you need to deal with flaky tests, which are a problem, often a bigger problem than you might think. At least we found we did some theses on that it's quite difficult to get reliable historic test information, because often you have some problems and then you make wrong connections between a test case and an area, kind of like when a test case failed in the past. And that makes this approach quite difficult because you need very clean data. If I understood correct what the approach you were suggesting, basically.
Yeah, that makes sense.
Yeah.
Thank you.
All right, thanks for the question.
Okay, I would say I will grab the screen shortly, and then we can have a look at the remaining questions. So I just take over the screen. Here we go. So first of all, I would like to say thank you to all of you for participating and asking questions, and also to our speakers. And as announced before, we will now launch the poll, and we would very much appreciate your feedback. So the poll should pop up in front of you. And as I said, there will be another survey opening up in the browser when you leave the meeting. And before we take the other questions, I have one more announcement. As you can see on my slide, we will have another talk coming up next week on Tuesday, and our colleague Sven will tell us how companies like Vestas, Dolby, and Rational have like 3 secret ingredients to build high-quality software. So that's really cool insights, and I think most of you are in the same time zone as we are, but if you're not, the talk will be in the morning in German time. But please just register anyways if this is inconvenient for you, and we will send you the recording. So I'd like to say goodbye and thank you again to everyone who has to leave now, and we will stay here for questions. And I have 2 questions, but they're quite long. So is there any question on the audio before we go into chat questions? So it doesn't seem to be the case. Okay, then I will read the long one out. So what is the different advantages and disadvantages between TeamScale and if the project has fully integrated Claude prompting with checks, new code, difference, and build tests on these changes? What is the effort of TeamScale? Claude, yes, the first run needs a lot of time, but if there still exist MD files, it runs a lot faster. And a very big, huge faster. So that was the question.
All right. I'm not sure if I understand the question fully, but I will try to answer it. And if not, then feel free to correct me. So my understanding is that you are using Claude to generate tests or actually to prioritize tests in some way, because if you are actually generating tests, then this will not really help with like your test suite will get bigger from that, and that's not what we're aiming for. We're aiming for making tests faster. If that is not the question, then feel free to correct me and let me know what you actually were asking. So I think the brief answer is we are addressing a different problem than Cloud Code does.
Okay, Sasha wrote, okay, thanks. So I guess the question is answered with that.
All right, great. Thanks for the question.
Then there is another question. Is there also a way to include the developer's inputs, which tests to include or include? And how does this apply to the efficiency situation?
Yes, you can always select tests manually to add on top of our list. So if you have specific tests that you think, for example, should always be executed, we had, for example, a customer who builds ATMs, and for example, the pin check should just always be tested no matter what, because if something goes wrong there, it's really bad. So let's be safe and run this test case every time. You can definitely do that. Just adding tests manually is technically easily possible. If you want more advanced input, then it depends, I would say. Like if you want input, not just selecting specific test cases, but having some specific criteria, I think I would need to know more, like what input would you like to give to the test selection. And what you can also already do is apply this selection only to a specific set of tests that you pre-select. So you can filter your tests already. If you say, for example, I only want tests from this package, or I only want tests from a specific part of my system, that you can already do to that type of input.
I don't get feedback back, so let's move on. And if there's any follow-up question, please just shout. And there's one more question. So this also acts as a Cube native orchestrator. And as in, we don't need additional configuration to run tests written cross-diff libraries.
I'm not sure I know all your terminology you're using. So you mean this handles Kubernetes orchestration, so starting up pods and things like that? Is that what the question is about?
Yes, sorry, to use short forms. Yes, what I meant was, do we need additional code to be able to run those tests that were written with, say, Playwright and Selenium WebDriver, or maybe Cypress or something else, another fourth thing. So if they were written across using different libraries, and then so I run it through test or team scale, and then would I still need additional sort of config in the YAML file to actually run the tests, or would TeamScale take care of triggering those tests?
Okay, all right. TeamScale is actually a passive component in that whole test environment, so it's only queried. So what essentially happens is while your CI is running, you send a query to TeamScale asking which tests are relevant now, or which tests should I run, especially for the change-based approach where you query every time. And then you get a list back of tests that are relevant here. And then basically the tests run as usual. You just run fewer of them. So just fewer tests running, but the same infrastructure, the same Playwright, Selenium, whatever you're using, the same Docker container or Kubernetes pods or infrastructure for your tests basically stays the same. TeamScale just selects the tests for you that should be run in this specific case.
Cool. That clarifies it. Thank you so much.
Okay, thanks for the question.
Okay, we have one more question in the chat. Are you looking for new team members? I'm working as a software tester, test engineer since 10 years, and you, the team, and your software sounds very great and interesting.
We're always happy to have excited people on board, but I'm afraid I'm not in the right position to answer that. I would have to hand that on to recruiting, but feel free to write to us.
Hey, thanks, Casper. Nice. I don't see any new questions in the chat, so anybody here who needs something else answered?
And thank you very much also from my side for the great questions and for listening to us talk for 1.5 hours.
And also from my side, thank you all for being here and for all your interesting questions.
So we get a lot of thank you and feedback back. That's great. And yeah, thanks also from my side. There was lots of interaction, which is really cool. And so, yeah, we are here for a couple of more minutes. So if anything comes to your mind, just stay with us. And otherwise, I wish you a great evening or morning, depending on where you're joining from. And hope to see you soon. Goodbye.